Hey guys, let's do 3-4b. We're going to start talking today about second derivative test. Now, we've talked a lot about first derivatives and second derivatives and what they tell us about our original function. We've talked about the first derivative telling us that our function is increasing or decreasing. If our first derivative is positive, then it's increasing. If our first derivative is negative, then our graph is decreasing. And then if it changes from increasing to decreasing, we know that we have a relative maximum there. If it goes from decreasing to increasing, then we know we have a relative minimum there, right? So first derivative tells us some stuff about our original function. We also started talking about our second derivative. And what does our second derivative tell us about our original function? It tells us it's concavity, right? If it's positive, if my second derivative values are positive, then that tells me that my function is concave up in that interval. If my second derivative values are negative, then that tells us that our function is concave down in that interval, right? What we're going to talk about today is how can we put those two pieces together to find more information out about our original function, okay? Second derivative test says two things. The first thing it says is if our derivative is 0. So what is happening when our first derivative, what's happening on our graph when our first derivative equals 0? It means there's a horizontal tangent there, right? We've been calling them swoopties, or maybe it just kind of horizontals off, I say. But there is some sort of a horizontal tangent there, right? Maybe a swoopty, we're not really sure, but there is some sort of a horizontal tangent where it kind of has a horizontal slope, right? But what if that happens and my second derivative is positive? What does it mean for my second derivative to be positive? It means that my graph is concave up there, right? And so if my first derivative equals 0 and my second derivative is positive, or my graph concaves up, what's happening? Doesn't my picture look like that? My first derivative is 0, there's a horizontal tangent. My second derivative is positive, so it's concave up. What does that mean has to be happening at that point right there? Doesn't f have to have a relative minimum at that point? So if I can figure out where my critical numbers are, where my first derivative equals 0 or doesn't exist, and then I can test those values in my second derivative. If those values are positive, then that means my graph is concave up. And that means I have to have a relative minimum there. Okay? So what do you think happens if my first derivative is 0? I have a possible swoopty. I have a horizontal tangent anyway. And then my second derivative is negative. What does that mean about my original graph? Doesn't it mean it's concave down there? And so what does that mean about this spot right here? Doesn't it mean that that has to be a relative maximum? That's what my second derivative test is. If I can find my critical numbers, and then I can plug those critical numbers into my second derivative. If my second derivative is positive, concave up, then that means I have a relative min. If my second derivative is negative, it's concave down, then that means I have a relative max. So I can find relative maximums or minimums two different ways now, right? I can test my sign chart and test my intervals and see if my first derivative changes from positive to negative or negative to positive, or I can do now my second derivative test and test my second derivative and see if it's concave up or concave down. Let's go ahead and practice second derivative test. This is kind of hard to see, but you have your examples out on your notes here. My function is f of x is equal to negative 3x to the fifth plus 5x to the third. And I want to see if there's any relative extrema. That means relative maximums or relative minimums, right? Before I can do anything with relative maximums or relative minimums, the first thing I need is my first derivative. I'm going to take my first derivative here and get me a negative 15x to the fourth plus 15x squared. And then I'm going to use my first derivative to find my critical numbers. Where does my first derivative equal 0? Where do I have possible swoopies, possible maximums or minimums? I'm going to set my first derivative equal to 0. I'm going to go ahead and GCF out a negative 15x squared. That's going to leave me here with an x squared minus 1. That means I have critical numbers at 0 and x equals plus or minus 1. Remember to add your plus or minus anytime you square root. So I have critical numbers at 0, negative 1, and positive 1. This is where my original graph is going to have horizontal tangents. Okay? But that doesn't necessarily mean there's a maximum or minimum there. Can I don't know, increase kind of have a horizontal tangent and then increase again. But this point right here isn't necessarily a maximum or a minimum, okay? There either has to be a sign change in my first derivative, or I have to test the concavity. If I know that it's concave down here, well then it has to be a swoopy, it has to be a relative max. Or if it's concave up here, then it has to be a swoopy or a concave up means there's a relative min there, right? So let's use our second derivative now, not our first derivative anymore. Let's use our second derivative to see if we can figure out if it's concave up or concave down. That'll help us figure out if it's a relative max or a relative min. My second derivative then from this function would be what? Negative, what's that, 60 x cubed plus 30x. Okay. I'm not going to set it equal to 0. What I'm going to do is I'm going to take this second derivative and I'm going to plug in my critical numbers. I'm going to take my critical numbers, my 0, my -1, and my +1, and I'm going to test those in my second derivative. I'm going to take my second derivative, I'm going to test -1, I'm going to test 0, and I'm going to test +1. Now, why do you think I'm going to test them in my second derivative? Because I want to see what's happening at -1. Is my graph concave up or concave down? In order to be able to figure that out, I've got to test it in my second derivative. So when I test a -1 in my second derivative here, -1 cubed is negative times a negative is a positive 60, right? If I plug in a negative here, I get -30, but that's still going to give me positive. So when x is -1, my second derivative is greater than 0, that means positive. If my second derivative is positive there, then what's going on my original graph right there? Aren't I concave up? So my graph ends up looking like that. So what's happening at x equals -1? Do I have a relative max or a relative min? Looks like I have a relative minimum, right? Let's go ahead and test +1. I'm going to skip 0 for a second. I'm going to test +1. +1 cubed is 1. 1 times -60 is -60. +1 and 30 is positive. -60 plus 30 is negative, right? So my second derivative is less than 0. It's negative. What does that mean is happening on my graph at x equals +1? Doesn't it mean my graph is concave down there? Which means look like that? So that point here, x equals 1, happens to be a relative maximum. Okay, let's go ahead and write that out. So I know here I have a relative, where should I put this? Let's go ahead and go down here. I have a relative minimum. What did we say? We have our relative minimum at x equals 1. -1, I mean. And we have a relative max at x equals +1. Now, if they wanted us to do points and we needed y values, again, how would we find y values? Wouldn't we have to plug that x, the -1 and the +1 back into my original, right? In order to be able to find points, I would need to plug them back into my original to find the y values. Okay, I'm going to go ahead and skip that for now. Let's not forget about our 0. And I saved 0 for a special reason. If you plug in 0 into your second derivative, what ends up happening? If I plug in 0 into my second derivative, what do I end up getting? I end up getting 0, don't I? So what does it mean about my graph if my second derivative is 0? It's not positive, not concave up, it's not negative, it's not concave down. What is it? It's kind of inconclusive, right? We're not really sure what it is if my second derivative is 0. So unfortunately, because my second derivative is 0, we're going to have to revert back to my first derivative and do my first derivative test when x equals 0. Meaning I want to test values on both sides in my first derivative. I want to test values on both sides in my first derivative so I can figure out if they're positive or negative. Remember, we're doing this in our first derivative now. If I were to plug in a, let's say, a -1 in my first derivative, If I plug in a negative 1, that's positive, times a negative 15 is negative 15. Oh, I plug in a 0, sorry. I didn't need to plug in a 1, I need to plug in a 0. I'm going to plug in a 0 to my first derivative. I end up getting what here? No, I do want to plug in negative 1. What am I doing? I'm sorry. I'm testing values, and let's test negative 1. Here we go. Come on, Mrs. Dummy. If I plug in a negative 1, negative 1 to the 4th power is positive 1. Positive 1 times negative 15 is negative 15. Is that right? If I plug in negative 1 here, I end up getting negative 1 squared is positive 1 plus 15. Don't I end up getting 0? What's going on here? Oh, because look at this. Don't I cross over another critical number? So that's the problem. I wasn't paying attention to that. Make sure you're paying attention to that so you don't do what I did. We have other critical numbers, don't we? At negative 1 and positive 1. So I can't necessarily test negative 1. What should I be testing? Shouldn't I be probably testing like a 1/2, negative 1/2 and positive 1/2? Okay? Go ahead and test that. Make sure you don't cross over any other critical numbers because that could change your behavior in your graph. So let's go ahead and test negative 1/2 and positive 1/2. Okay? If you do that in your first derivative, you end up getting a positive here and a positive here. That means I'm increasing on both sides. So do I have a relative max or a relative min at x equals 0? It was a trick question. You don't have either, right? If you don't change from increasing to decreasing or from decreasing to increasing, if you stay increasing the whole entire time, x equals 0 is not a relative min or a relative max. But the only way that you could have figured that out is by plugging it into your first derivative. So on this graph, you only have one relative min at x equals negative 1 and one relative max at x equals positive 1. Okay? All using my second derivative for those two. Okay? Let's practice another one. I kind of ran out of room here, so let me bring this. Let's bring this one down here and do this example. It says f of x is equal to x to the 5th minus 5x to the 4th. Let's first find our first derivative. I find my first derivative so that I can find my critical numbers. I have 5x to the 4th minus 20x cubed. I want to take that first derivative and set it equal to 0 so I can find my critical numbers. I'm going to factor out a 5x cubed, leaving me with an x minus 4. And I get critical numbers at 0 and 4. 0 and 4 will be my critical numbers. That's why I have possible maximums or minimums. But I don't know for sure unless I start testing some values. But I don't want to use my first derivative. I want to get used to using my second derivative also if I need to. So let's go ahead and find my second derivative. My second derivative would be 20x cubed minus 60x squared, right? All right, so that's my second derivative. Now I want to test my critical numbers in my second derivative. All right, so if I plug in a 0, what do I end up getting? In my second derivative, I end up getting 0. That means it's not concave up, it's not concave down, it's kind of inconclusive, so we have to hold off for a second. What if I test 4? If I test 4 in my original, or not my original, my second derivative, I end up getting 320. That's greater than 0, right? It's positive, which means I'm concave up. If I'm concave up there, what does that make x equals 4? Doesn't it make it a relative minimum? A relative minimum at x equals 4? All right, and I can find the y value again if I needed to by plugging it into my original. I'll save that for you. Let's go back to 0 though. We got to figure out if it's nothing or if it is something. But we can't use our second derivative because that came back inconclusive. So let's use our first derivative. Okay, be careful of my other critical numbers. Remember how I messed up last time? The only other one I have though is 4, right? So now I can use whatever numbers, negative 1, positive 1. Let's test it in our first derivative this time. If I test it in my first derivative, if I test a negative 1, I end up getting positive on this side. If I test positive 1, I end up getting 5 minus 1. I'm getting negative on that side, right? So what does that mean about my graph from negative infinity to 0? What's the behavior going on there if my first derivative is positive? Doesn't that mean increasing? Right? Because we're first derivative now. If I'm negative in my first derivative, that means I'm decreasing. So what does that make x equals 0? If I'm increasing then decreasing, doesn't that make x equals 0 a relative maximum? It's a relative maximum at x equals 0. You can find the y value by plugging it into your original, but I can only figure out that it was a relative maximum by reverting back to my first derivative test. So sometimes second derivative test doesn't work. Just because it doesn't work, though, doesn't mean it's nothing. You might have to figure out what it is by going back to your first derivative. Okay? All right, so we found our first derivative. We set it equal to 0 and does not exist to find critical numbers. We then took those critical numbers and plugged them into our second derivative so we can figure out the concavity, concave up versus concave down, and that'll help us figure out if it's a relative max or relative min. All right? All right. Next thing we're going to do, you'll see this a lot on the AP test, is they'll give you certain characteristics of a graph, and then they're going to want you to put it all together and see if you can graph this thing. Okay? We're going to sketch the graph with the given characteristics. So let's talk about what each of these things mean first. The first thing I see is f of 0 and f of 2 are equal to each other, and they both equal 0. What is that really saying? So the big thing here is, do you know what notation means? Okay, and can you interpret it and put it onto a graph? So what does it mean for f of 0 to equal 0? Doesn't that just mean I have a point on the graph at 0, 0? And what does it mean for f of 2 to equal 0? Doesn't it also just mean I have a point on the graph at 2, 0? So I know that on my graph I have a point at the origin, 0, 0, and then I also have a point at 2, 0. Okay? The second thing that it tells us is that my first derivative is negative. What does it mean on my original function for my first derivative to be negative? What does first derivative tell us? Increase, decrease, right? And so if it's negative, then I know that my graph should be decreasing when? For all values less than 1. So my graph is decreasing for all values that are less than 1. So to the left of 1, my graph should be decreasing. All right. What does it mean for my first derivative to equal 0 at x equals 1? That's what that's saying, right? My first derivative equals 0 at x equals 1. What's happening at x equals 1 then? My first derivative equals 0. Doesn't that mean that there's some sort of a horizontal tangent, right? So I know that there is a horizontal tangent at x equals 1. Okay? All right. The next thing, what does it mean for my first derivative to be positive? Well, first derivative means increase, decrease. So if I'm positive, then that means I should be increasing, and I'm increasing wherever x is greater than 1. So before 1, I'm decreasing. At 1, I have a horizontal tangent, a swoopty, and then after 1, I'm increasing. So visualize what that might look like. Okay? The last thing I need is I need for my second derivative to be positive. What does it mean for my second derivative to be positive? My second derivative is positive. Second derivative tells us concavity. So if I'm positive, then that means I'm concave up. And it doesn't give me a specific time, so it looks like I'm concave up everywhere. So now that I have these things, these characteristics, can I piece them all together and kind of sketch what this graph might look like? The first thing, I have a point at 0, 0. We also said we have a point at 2, 0. Okay? At x equals 1, so here's 1, and from the left of it I'm decreasing. So to the left of this little dot right here, I should be going down. At 1, what's happening? At 1, I have a horizontal tangent or a swoopty, because after that I increase, right? And I'm supposed to be concave up, so maybe my graph goes like this. It goes through 0, 0. It's decreasing, it decreases, it decreases. It has a horizontal tangent there. Then it increases, 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 and goes through the point 2, 0. let's make sure that all my characteristics work. I have my 2 points? Yep. Am I decreasing until I hit 1? Yep. Do I have a horizontal tangent at 1? Yep. Do I increase after 1? And is my whole entire graph concave up? Perfect. All right. So make sure you know all the different notations. Can you interpret what they mean about a graph? Increase, decrease, horizontal tangent, a swoop-D. Do I concave up, concave down? And then can you put them all together just right so that it matches what that graph might look like? Okay? All right. We're going to go ahead and pause that for right now. We'll see you tomorrow.